In this video lesson, we are going to revisit double replacement reactions, which is a topic we learned about earlier this year. But now we are going to fold into this topic how solubility plays a part in deciding what's going on with the products. Ionic compounds are generally soluble in water, but not all of them are soluble. We'll be using reference table F, this right here, to help us determine if a compound will dissolve in water, right? And so what we're going to do is we will need to decide if a substance is soluble or not. If it is insoluble, we're going to put an X over the arrow. And if it is soluble, we're going to do three things. We're going to use the periodic table and reference table E to determine the charge on the dissociated ions. And we're then going to balance the equation by putting the appropriate coefficient in front of the dissociated ions, and then use the proper state of matter symbols on each species. So what we are trying to do, before we can predict the products of a double replacement reaction, we have to start by looking at an ionic compound, separating it into its ions, and then figuring out what charge they have. So Ki is going to turn into K with a charge of +1 and iodide with a charge of -1. If I use reference table F, right, potassium is a group 1 ion, right? Potassium is a group 1 ion. Group 1 ions are always soluble, so this will indeed, Ki will dissociate or dissolve into 1 potassium ion and 1 iodide ion. Because it is soluble, we are going to state that by saying aqueous and aqueous, assuming we are starting with a solid reactant. Okay. So if we're starting with barium nitrate, right, before we decide what these ions are, we should really check to see the status of its solubility. Will it even dissolve into ions? And because it has a nitrate ion, we know indeed that this will dissolve. Nitrate is always soluble with no exceptions. Okay, so let's take a look here. Barium is going to have a charge of +2. Nitrate, as we saw right here, has a charge of -1. But you can see here that we had to have 2 of these nitrate groups. So I'm going to put a 2 in front of there, and this is going to be 1. And because we did decide it was soluble, we're going to say that these ions are indeed aqueous. All right, next on the list is ammonium phosphate. Here we have ammonium. Ammonium is always soluble, so this will indeed happen. I notice right now that ammonium has a +1 charge. I notice that there are 3 of them, so I'm going to put a 3. When I separate this apart, I'm going to notice that I have 3 individual ammonium ions. And then PO4, right, which is the phosphate ion, it has a -3 charge. And there's just 1 of them. There's just 1. And because it is soluble, we will say that it is aqueous. All right, PbCl2. I notice that this substance has Cl in it, right? And so Cl is soluble, except one of the exceptions is when it's with lead. So this will not dissolve, right? And we're just going to put an X through it and we're done. We're not going to dissolve. We're not going to separate it into its ions because it didn't dissolve. MgCl2. Chlorides are soluble. Magnesium is not an exception. So this solid will indeed split apart into magnesium ions. Magnesiums are a +2 ion. They will become aqueous. And I notice I will have chlorides. Each chloride is a -1 ion, right? The -1 are taking that charge at the very top up there. Also aqueous. And if I look at my total numbers, I had 2 of these chlorides, which makes sense because each one was a -1 charge. All right, let's take a look at barium sulfate. Barium sulfate, we have to look to see if it's soluble. Sulfates are soluble except, barium is an exception, so that makes barium sulfate insoluble, right? And therefore, we're not going to write a dissociation equation. K2S. K is potassium. It is a group 1 ion, right? It is in group 1. So group 1 ions are always soluble, which means I need to separate this out. I know that potassium ions are going to separate out into +1 ions. Sulfide ions are going to be -2 ions. I had 2 total of these potassium ions. I had 1 sulfide ion, and because it was soluble, we'll say that this solid did dissociate into 2 aqueous ions. Calcium hydroxide, let's see if it's soluble. Hydroxides are insoluble, except when calcium is attached to it, so that is soluble, which means we're going to have a calcium ion. Calcium ion is a +2. And hydroxide, right? Hydroxide is OH with a -1 charge. There are 2 of those hydroxides, and there's 1 calcium. So calcium hydroxide as a solid will dissolve into calcium ions and hydroxide ions. So we are starting here with, these are called dissociation reactions. Okay, dissociation. It's basically showing the dissolving of soluble ionic compounds. Okay, let's take a look and see what we're going to do with this. Once we can figure out if a compound is soluble or not, then we can see what it's going to do in a double replacement reaction. Okay. A double replacement reaction, as you recall, is when you have a soluble compound like AB, right? This is an ionic compound, reacting with another soluble ionic compound, okay, also ionic, right? It's soluble, so I'm going to say that it's going to become aqueous. Now, what will happen, remember, in an ionic compound, the metal is always written first, the nonmetal is written second. Metal first, nonmetal second. So when we make our new combinations, because we're going to get a partner swap here, the metal A is going to now connect to the nonmetal D, and the metal C is going to now connect with the nonmetal B. Okay. One of these will remain aqueous, right? One of these will remain soluble. The other one will be insoluble. And in which case, that means it will form what is called a precipitate, and it will come out of solution as a solid. So things to note about these double replacement reactions: both reactants will always be soluble compounds. That means we will always use the aqueous state of matter. One of the products will be an insoluble compound. That means it is called a precipitate, and we'll use this state of matter, right, which stands for solid. The other product will be a soluble compound, and therefore we will use the aqueous state of matter to follow it. So here's what's going to happen. You'll be given reactants, and you're going to have to predict the products. So what you will do is you will start by dissolving each compound into its ions, including their charges. Do this underneath or above or wherever you have space to kind of scratch out your work. You would need to have reference table E in the periodic table to help you with charges and formulas. So here I see that I have 2 lithiums. Each lithium is a +1 ion, right? I'm just getting that from here. CO3 is carbonate, right? Carbonate is CO3 with a -2 charge, right? And it's aqueous, so we know, they're telling us it's aqueous, they're telling us it's going to dissolve. We know we're going to get, out of this, we'll get 2 lithium ions and we'll get a carbonate ion. AgNO3, also aqueous. Here's what we're going to get out of it. I see 1 silver ion, Ag. The charge on a silver ion is Ag plus 1. NO3 is nitrate. It is NO3 with a -1 charge. Right? So I'm going to get 1 of these silvers and 1 of these nitrate ions. Okay? So once I know what my initial compounds dissolve into, then it's pretty easy to make new combinations. And the only thing we have to watch out for is to neutralize the new compound formula by drop and swap. And we will write those neutralized formulas on the product side, which of course is the right side of the arrow. We'll then need to figure out the solubility of each of those new substances by using table F, and then we balance the equation with coefficients. So let's take a look at our new combinations. I'm going to put lithium, and I'm going to do my scratch work underneath. I'm going to take 1 of those lithium ions, and I'm going to partner it up, not with carbonate, because that's who lithium came to this reaction with. I'm not going to partner up lithium with silver, because they're both positively charged. I'm going to partner up lithium with a nitrate ion. So lithium's a +1, nitrate's a -1. That makes the formula just 1 of each, LiNO3. Okay, now my other combination is going to be, I'm going to start with my silver +1 ion, and the only other ion I can pair it with now is the carbonate ion, CO3 with a -2, right? And so because it's a +1, -2, the formula I'm going to write up here is Ag2CO3. Okay. So I've made the new combinations. I dropped and swapped to make sure that the new compound formula is neutral. And now I need to go write the states of matter after the product formulas. Anything with a lithium or anything with a nitrate is going to be soluble and therefore aqueous. Ag2CO3. CO3 is carbonate. Carbonates are insoluble unless they're paired with a group 1 ion or ammonium, which in this case that is not the case. So this Ag2CO3 is the insoluble, and therefore it is solid. That's an S for solid, and that means it will precipitate out. Lastly, I would go through and balance the equations. I see that I have 2 lithiums on the left, so I have to put a 2 in front of the LiNO3 on the right. I have 1 carbonate group on the left, 1 carbonate group on the right. 1 silver on the left, 2 silvers on the right, so I'm going to put a 2 in front of the AgNO3. That's going to give me 2 nitrate groups, but I have 2 nitrate groups, so there you have it. We have predicted the product formulas. We have determined the product solubilities, and we have balanced the equation. The remaining page here is meant for you to work through these problems. So I'm going to work through these relatively quickly. I won't do too much explaining, but if you are watching this video, maybe pause the video, try it on your own, and just turn on the video when you're looking to either verify your answer or you are looking for help in understanding how to do it. So I'll try to narrate a little bit as I go. AgNO3 is going to separate into those 2 ions. Potassium chloride is going to separate into K+ and Cl-. The new combinations are going to be AgCl plus KNO3. KNO3, any nitrate, any group 1 group 1 ion will be aqueous because it's soluble. AgCl, chlorides are soluble except silver is an exception, so this is going to be the precipitate. And I believe this equation is just naturally balanced. Example number 2. FeBr is going to separate into iron plus 2 and bromide ions, Br minus 1s. K2CO3 is going to separate into potassium ions and carbonate ions. The new combinations are going to be the Fe plus 2, CO3 minus 2, so just FeCO3 plus KBr. Potassium group 1 ion will be always soluble. Carbonate, double checking, insoluble except with a group 1 ion or ammonium, which this is not the case. So this indeed is going to be our precipitate. If I balance the equations, it looks like I'm going to need a 2 in front of the KBr, and everything else is balanced. Example number 3. We're going to have copper plus 2 and S minus 2. KCl, K plus, Cl minus. My new combinations are going to be the K, the potassium plus 1 and the sulfide minus 2, so that's going to be K2S, plus CuCl2. Anything with a potassium is going to be aqueous. Chlorides are soluble. The exceptions are silver, lead, or mercury, so copper is not an exception. So this is actually also aqueous. And we're going to go through and balance this because I think we're going to need to have a 2 here, and that's going to fix everything else. But in reality, this reaction doesn't really react because there's no precipitate. So if you start with these aqueous solutions, you're just going to end up with aqueous ions. Nothing precipitates out, so we say that there's no reaction. It was good practice, though. Last example, we've got calcium plus 2 ions, hydroxide minus 1 ions. In our next reactant, we have magnesium plus 2 ions, and we have acetate ions, C2H3O2 minus 1. All of those can be found on reference table E if you're not sure where those came from. Making our new combinations, I'm going to put magnesium together with hydroxide, so that's going to be MgOH2 plus. I'm going to put the calcium together with the acetate and get Ca C2H3O2 2. Solubilities. Acetates are always soluble, no exceptions. So this substance is going to be our aqueous ion. This magnesium hydroxides are insoluble. Magnesium is not an exception. So that means MgOH is insoluble and therefore our solid precipitate. If I balance each one of these, it looks like, oh, it's already balanced. These are all 1s for coefficients. All right, so this reaction does react because we do produce a solid precipitate. All right, so in this lesson, what we have done in order to predict products of a double replacement reaction, we had to start by looking at our reactants and figuring out how do we show this chemical dissolving into its ions. Right, so we spent some time taking an ionic compound and trying to figure out what ions were present when we dissolve it into water. Once we did that, we figured out how to make our new combinations. We did the drop and swap to figure out neutral compounds. We then gave us our formulas, our predicted formulas for a double replacement reaction. We then had to use reference table F to determine the solubilities of those products to determine if a precipitate forms or not. And then we did go through and balance those equations as practice with that skill. All right, that's it for this video lesson. I will see you back in the classroom.